Hello, everyone. It's wonderful to see you, everyone. This is our penultimate session of 2020. And we're very excited to have Iris here. Do you guys see or hear me? Could you please say something in the chat so I know how long the delay is? If you can hear me, send the smoke signal. Or the like. Okay. It seems like there's yes. Okay, perfect. They can see us. All right. So we're delighted to have you here. This is our 14th session of the Learning Salon. And the Learning Salon is a weekly gathering where you can sort of gather with friends and colleagues to discuss the contentions and bridges between biological and artificial learning. We are respectful to each other, and we sort of go by the rule of kindness, as well as intellectual, rigorous discussions. So very, very welcome to intellectually disagree with each other, but no one-upmanship or disrespect or sort of making fun of each other, please. And we try to have a flat hierarchy and socially progressive norms. So hi, Jeremy Manning. I'm glad you joined us. This is Jeremy's first time joining us because he's taking care of his kid at this time usually. So he might appear on screen at some point with his child. And also, I want to just say that if you're a person that's not very familiar with the field, or if you're a junior scientist, you're a student, you should still feel free to speak up and ask a question. We try to have a flat hierarchy here. You can ask your question in the Ask a Question area below the screen. You can ask your clarification questions in the chat area. And it's a privilege to have you guys here as our community on a weekly basis. We usually like to say that it's a different skill to be smart on paper and read and ask questions within a lot of times at the end of talks and seminars in universities, which is like 2 or 3 questions sometimes. It's an entirely different skill to have multidisciplinary conversations with everyone and really discuss where we are at. And so we're hoping to promote that kind of a conversation. Kanaka, Brad, Claire, and Eva are behind the scenes helping us, and Kanaka and Brad in the chat will answer some clarification questions you might have. And yeah, so we're very privileged and excited to be here. Before, I guess John will be introducing Iris, or is it Jovo?
I am?
I don't know. Is it Jovo? Then I guess it's Jovo. It's Jovo's turn. Yeah. You introduced last week, so it's Jovo's turn. So before introducing, yes. Oh, thanks. He even muted himself. So before introducing Iris, I just want to say the neuroscience community lost a shining star last weekend. For some of us, a friend, someone that I knew since 2013. And although we weren't in the same institution for, I guess, 3 or 4 years, we were still in touch until a month ago. And Christina Damisoro passed away last weekend. And I had a lot of conversations with her about science and about life, and she was an exceptional human being, very fond of nature and scavenger hunts. She had a nature paper that was very fantastic during her PhD. She was brilliant, and she was very hard on herself, but the academic world was very cruel to her. And so I am very much at a loss of how to process this, to be honest with you. And I have been crying all week. So just want to celebrate her life for a moment right now. And to everyone who knew her, she's well remembered. And we've all been reaching out to each other, but yeah, hopefully I'll have a better idea of how to celebrate her life once we talk to her family. It's a loss for all of the Princeton community who knew her. It's a loss for the Champollion institution and every other institution where she's been at. Everyone who saw her was touched by her passion for life and science and by her unapologetically peculiar magical presence. She used to like to sit on floors and on top of tables like a cat a little bit, and she scared a lot of people at Princeton because they didn't see her, and she was a joy to have around and talk to. Many late night conversations. Okay, so with that, Jovo, could you please introduce Iris?
I will try. Thank you, Ida. That was really beautiful and touching. So Iris, for those of you who don't know her, although I think probably everyone does, she's done so much brilliant work over the years. When Ida introduces people, she likes to say their affiliations and awards and things. I just like to say something personal about them and how they've touched me. And I'll just say, I've been reading Iris's work the last several months, and it's really amazing. And I don't know if Iris, this is your intention when you write, but somehow I feel when I read your writing that you're deeply invested in my personal understanding of the words that you write in a way that, it's complexity theory. It's not, it's not a novel, and yet I feel touched by your compassion in your writing, and it's just so amazing and so beautiful and so inspiring. I'm just so excited to talk to you about it. I'm so excited to have you here. So thank you so much for joining us, and we're so excited to hear what you have to say.
Thanks. Thank you for those words. So I share now.
Please.
Do that? Yeah.
Yes.
So let me see. Okay. Can I check if you still hear me?
We can hear you.
Ah, perfect. Yeah, because I cannot see you anymore. Yeah, thank you, Jovo. Those are beautiful words. I'm also very excited to be here and finally to be on the Salon and to be discussing with you afterwards. I'm very much looking forward to that. Okay, so let's dive in. So my talk is titled Why Cognitive Scientists Should Care About Computational Complexity. And I should say from the start that this title is inspired actually by a title from a paper by Scott Aronson, which is Why Philosophers Should Care About Computational Complexity. And I creatively adopted it, and I will be focusing on why cognitive scientists should. Okay, so there may be many reasons why cognitive scientists may care about computational complexity, but I will focus here on two reasons, specifically related to that. I think that unaided by insights and the techniques and concepts from computational complexity, our intuitions sometimes about models may go astray. And I will be focusing here on two ways in which they can. First of all, we may have incorrect intuitions about whether or not models that we make of cognition scale to the real world. So we may, for instance, incorrectly intuit that a model that works for a toy domain also will approximately work in the real world. Having figured out or discovering that actually this is not the case, we may have a second wrong intuition, namely about ideas, what would make our models actually scale? So even if we realize that our models don't scale to the real world, we may also have incorrect intuitions about what could possibly make them scale. Okay, so what do I mean by scaling models of cognition? So as practicing cognitive scientists, we are interested in understanding, I think, ultimately cognition in the wild. So humans going around their business, they demonstrate all kinds of remarkable cognitive capacities, including communication, perception, decision-making. And as cognitive scientists, we want to understand how these capacities work and how we can explain them. So how do we go about doing that? Well, usually we try and bring these capacities into the lab. We come up with sort of toy domains or particular tasks that we believe sort of capture the essence of these capacities. And doing so, we gain experimental control and we can test behavior under different conditions. And ultimately, we may even be able to model this behavior. So this is all good, but I think that seldom in cognitive science we ask of a model if it performs very well or it fits well observations of tasks in the lab, whether or not that model actually also can scale back to the real world to actually explain the capacities as they occur in a natural complex setting, not just in the toy domains that we constructed. Now, there may be different reasons why a model may not scale back, and here I focus on one such reason, namely if a model happens to be intractable, then it will not scale back from a toy domain to the complex real world. Now, okay, so some of you may think, well, what is this intractability and why is it a problem? And I like to explain that using a quote. And this is a quote from Gerd Gigerenzer and colleagues. And it goes as follows. The computations postulated by a model of cognition need to be tractable in the real world in which people live, not only in the small world of an experiment. This eliminates empty-hard models that lead to computational explosion. Now, this quote, in a nutshell, explains the problem, but in order to actually grasp it, I think it's useful to unpack it a bit and maybe also define some of the key terms in this quote. So let me start by saying what I will mean by model of cognition in the context of this talk or this argument. By a model of cognition here specifically, I will mean a computational level model. And in this crowd, I assume that Mars 3 levels are familiar. So I won't need to go into too much detail, but just briefly to remind you, at the computational level, a model merely specifies the function that is believed to characterize the capacity. So this specifies the input-output mapping, the function, or computational problem, if you will. Having postulated such a computational level model, cognitive scientists may go on to ask, okay, what is then the algorithm by which this computation is computed? And having such an algorithm, one may further go on to ask, well, how is that algorithm physically realized? It's known that in this scheme of explanations, there is an underdetermination of lower level explanations by higher level explanations. And by this I mean that given a particular function postulated at the computational level, there can be multiple algorithms consistent with this computational level theory, all of which would compute that function. And also, given a particular algorithm, there can be different physical realizations that all implement the same algorithm. And this possibility, of course, gave rise to the idea that we can physically realize human cognitive capacities in other substances than, for instance, human brains. Now, so I will be focusing on computational level theories here because this is where this property of intractability applies to. But I should say that what I have to say is neutral about the kinds of cognitive modeling framework you would like to use. And it's also, in a sense, neutral to what kind of physical system you're interested in. So what I'm going to say is going to apply to whatever modeling framework is your favorite modeling framework. And also, it may apply for individual cognition, but it can also apply to group cognition, or it could even apply to things like evolutionary processes. We can discuss this maybe later. Okay, so back to the quote. So having clarified what I mean by model of cognition, now there's this other important term there, MP hardness. What is that? And what's that? That it leads to computational explosion. So let me explain that next. The notion of MP hardness, it has a precise formal definition, but I cannot go into that here. But for our purposes, it suffices to say that MP hard functions cannot be computed by any polynomial time algorithm. There's a background assumption, the P is not equal to MP assumption, which is in fact a $1 million question. And my training demands that I explicate this assumption, but otherwise it will just be in the background. Okay, so since MP hard functions cannot be computed by any polynomial time algorithm, they will require for their solution intrinsically more than polynomial time. So for instance, exponential time or more. And this is why MP hard functions are considered intractable. In other words, they are unrealistic to compute for all but small inputs. And that is illustrated here by these two tables. So on the left, you see an illustration of so-called polynomial running time, and on the right, a non-polynomial one, an exponential one. And here n is some measure of the input size of the problem. As you can see, for small n, actually the two kinds of computations, computational complexities, they don't differ that much. But as the input size grows very quickly already, exponential running time becomes very unrealistic, very fast. And for instance, if you take an n is 1,000, I don't know how well your intuitions are of exponential growth or these large numbers, but for such a computation, even if we had as many parallel channels in our brain as atoms in the universe, it would take longer than the time that has passed since the birth of the universe to actually complete such a computation. Okay, so the upshot of this is that while a polynomial time computation may still be plausible as an account of a human cognitive capacity, non-polynomial time computations, they become well, explosively, they require an explosive amount of time for their completion, and so are very unrealistic in that sense. I want to clarify that this distinction between problems that intrinsically require exponential time versus those that can be solved using polynomial time is presumably, at least according to the invariance thesis, not sensitive to the computation model that you use, sort of the mathematical model of what it means for a system to compute. So this distinction doesn't only hold for sort of classical Turing machines, but also for neural networks, cellular automata, even quantum computers, and according to the invariance thesis, for any reasonable, plausible model of brain computation we may come up with. Okay, so back to the quote. So I've explained model of cognition, I've explained what's MP hard and why MP hard problems lead to this problem of computational explosion. And now here's a key part in the quote, namely that computations postulated by model of cognition need to be tractable in the real world in which people live, not only in the small world of an experiment. Okay, so to bring this point home, so imagine that you're studying a cognitive capacity and you come up with some, say, Bayesian model of it. It doesn't matter, it's just for purpose of example. And you succeed in modeling this task, and your model is intractable, then you may experience a small explosion, but since you're only dealing with a toy domain, this doesn't bother you too much. But if you were to actually scale up this model to deal with inputs of realistic size and complexity, then actually this computational explosion will bite you. Okay, now I want to note that, so I use the Bayesian model as example, but in fact, this problem of intractability, it is quite widespread. Actually, if you take modeling frameworks of any generality, usually you run into intractability problems if you scale up models to real-world complexity. And this is, for instance, illustrated by this table. This is just a selection of models or frameworks, just to illustrate the point that this problem of intractability is not specific to any particular cognitive capacity, and it's also not specific to any particular modeling framework. So both in Bayesian models or in connectionist models or in logical models, you see examples of intractable problems. Okay, so now a question is, how have cognitive scientists been dealing with intractability? Or rather, as I argue, how have they not been dealing with intractability? And how cognitive scientists deal with intractability seems to often depend a bit to what extent intractability is observed in someone else's model or in their own model. So for instance, when intractability is observed in someone else's model, then a common response to intractability is what I call finger pointing or framework rejection. Basically saying, well, the model in your framework has this problem, so I think therefore your framework is bad. And if we look at the history of cognitive science, we see that, for instance, traditionally, connectionist modelers and Bayesian modelers have pointed to more classical logic-based models and saying, well, these problems, they have this problem of intractability. And this is why we are a better framework for modeling cognition. Until, of course, it became clear that also in connectionist and Bayesian frameworks, we run up against intractability. Similarly, proponents of heuristics-based models or dynamical systems models have pointed fingers at more classical models of cognition. But ultimately, in all these frameworks, if you want to scale them up, you actually run often into this problem of intractability. And we've pointed this out in several publications. Okay, so the pointing fingers or the framework rejection is a common response to actually try and make one's own framework look better and point the finger at another. But when the problem is found, intractability is found in one's own modeling framework, there are different kinds of strategies or coping strategies. And I think often they're basically different variants of objections saying, well, I don't really have a problem because of X, Y, Z objection. In our book, actually, we cover, I think now 14 different objections, and I cannot, of course, list them all here. Maybe they come up in discussion. I'm actually pretty sure some of them will be raised, and I look forward to discussing them. But let me at least pick two to illustrate the form these objections can take, and also to illustrate how one can actually show why they don't hold water. So the heuristics objection first. So the heuristics objection takes the following form. A cognitive scientist may discover that they have a computational level theory that is intractable and say, well, but I don't really have a problem because although I realize I cannot have a tractable algorithm for this computational level theory, that's not possible since the computational level theory is intractable. But what I can have is a tractable heuristic. And this tractable heuristic, it doesn't compute the function postulated at the computational level exactly, but it may compute it well enough or often enough. Now, a problem with this coping strategy is that since the heuristic is not an exact algorithm for the function postulated at the computational level, there must exist inputs, and in fact there must exist infinitely many inputs, for which the output of the heuristic is different from the output postulated by the computational level theory. And this is problematic, at least in two ways. Well, first of all, for all these inputs, of which there are infinitely many, the heuristic actually fails to explain how the function at the computational level is computed, because it doesn't compute them. And also there's a problem in terms of confirmation or testing of the theory, because there will be, again, infinitely many inputs where the computational level theory and the algorithmic level theory actually make different predictions. And so if you would confirm the one, then you actually disconfirm the other. Now, a follow-up on this may be that, well, okay, maybe the heuristic is not an exact algorithm. Sorry, there's the inconsistency. I forgot to put it up. But maybe it's an approximation algorithm in that, okay, it doesn't exactly compute the function postulated at the computational level, but it does so approximately, in the sense that the difference between the two computations is arguably small, so small that for all intents and purposes, you say, well, this is a good approximation. And one may argue, well, models are approximations of reality anyway, so why wouldn't we allow this kind of approximation relationship between different levels of explanation? And I'd agree. I think that is a fair response. But this assumes that approximating intractable functions is tractable. And in fact, most of the time, it isn't. So, for instance, if we take again Bayesian inference, known to be intractable for exact computation, is actually provably also intractable to approximate, according to different kinds of definitions of approximation. Now, that doesn't mean that there isn't any possible notion of approximation for which such a computation could be tractable, but actually demonstrating that that is the case requires using the tools of computational complexity theory to actually prove that that is the case, because it cannot be assumed intuitively to hold across the board. Okay, so I'm told that after bringing all kinds of bad news, I also have to bring some good news. So let me end with also a positive note on how computer scientists could be dealing with intractability in a systematic way. And for this, and we also discussed this in our book, I propose that we can adopt the tools of parameterized complexity theory to use what I call the parameterized approach to dealing with intractability. Now, this approach is based on the insight that even though a computational problem may be NP-hard, and so there exists no polynomial time algorithm for solving it, the problem may still be what we call fixed parameter tractable. That means that actually the exponential part may be possible to be confined in certain parameters of the input. And what are parameters? Well, parameters could be any property of the input. So for instance, if I have a Bayesian network like here, a parameter could be the number of observed nodes, or the number of hypothesis nodes, or the in degree, or the out degree, or any graph property really, like the longest path in the graph, or tree width. And for any such parameter, one could assess whether or not it's possible to actually compute the function in a way where the exponential complexity or the explosion, say, is confined only as a function of these parameters, while the rest of the computation time is polynomial in the rest of the input. And if that is the case, and sometimes it is, provably so, then if we were to assume that for ecologically relevant inputs, these parameters are small, then actually also this explosion remains very small. And we can still tractably compute for very big inputs an otherwise intractable computation. Of course, if this is the case, and we want to make use of this assumption, we will need to constrain our model to explicitly assume small values for these particular parameters that make the problem a so-called fixed parameter tractable. Now, this of course could always be done, but we need to verify whether or not these assumptions indeed hold in real-world situations. And also we can test in the lab, if we adapt our theories in this way, whether or not indeed human performance breaks down if we artificially manipulate these parameters to bigger values. We can actually probe to see if indeed human performance is sensitive to these parameters in the way that the theory predicts. Okay, so with that, I have come to the end of the presentation. Let me end with the conclusions that I think cognitive scientists should care about computational complexity. And here's my summary of why that is the case. Because intractability prohibits models to scale to the real world, but also that our intuitions about intractability can be wrong. And therefore, we need to use formal tools from computational complex theory to actually verify our intuitions and to constrain our models. Okay, with that, thank you very much. And I look forward to questions and a discussion.
Thank you so much, Iris. This is fantastic. Such a great presentation, great talk. And I think, okay, I see that there are some questions. And I think as we ask you our questions, people will have some time to also enter more questions. Okay, so everybody's clapping hand for you. And we're very excited about your talk. It was fantastic. So I have a lot of questions, but I'm going to first wait for John and Jovo.
Why?
Okay.
Just go.
Because in a couple of sessions, I started asking first, so I thought maybe this time it's your turn, but I could go first.
You should go first. Cheer yourself up.
Okay. Assuming this cheers me up. Okay, so I really appreciated this. I'll start with just maybe a little bit more specific question. So there are a lot of computational models of various modes of cognition, say of memory. There are many computational models of memory. There are many other models. They're usually built in cognitive science or in psychology to fit a particular type of behavior or a particular type of cognitive task or cognitive test. And they are commonly good at making some predictions about some outcomes of next experiments. So some of them have survived the test of time for like 20 years, some of them more, some of them less. And sometimes they compete with one another, and then someone designs an experiment and can compare them. But there is not a lot of concern about their sort of computational complexity. And I think that that's something that, so John Langford and I have talked about this a lot, that we should be sort of concerned about this. Even when we are making a model for a simple task, is this model sort of, is it order n? Is it quadratic? What is the computational complexity of this for storage? What is it for retrieval? How does this computational complexity affect its retrieval? And can you make sort of predictions of that? So how do you think for existing models in cognitive science and psychology that didn't have this concern in mind, how do you think we can address their computational complexity and compare them in this regard?
You're asking me, Ida, to how? I'm not sure if I understand the how. How can we? I think
so these are specific models that, right. These are specific models for specific tasks when there aren't many items. So they're not made for scale, but there are claims of their generality.
Indeed. But
yeah,
if there's claim for the generality, then my recommendation would be is to explicate those claims. So yeah, I think often if psychologists or computational modelers, they make their model for a particular task. But also if you read the introduction, the idea is that this is just one instantiation of a general capacity. And it just has this particular form because of the task. But the idea is that this task indeed captures the key properties of the general capacity, for instance, of memory. And your question to me is how could they actually think about the computational complexity of their own models? Oh, hi! Gezellig, we would say in Dutch. Yeah. So back to your question. Okay, two angles. The one is in order to use computational complexity tools, we need to have formal theories. We cannot apply them to informal intuitions. And I think currently, too often, if you're lucky, there is a model, but the model is only about the task. And what the general capacity is, of which this is presumed to be the instantiation, is only described informally. And in order to apply the tools, this should also be described formally. And then it can be analyzed for its computational complexity. But I think often it isn't done. But there's also other, I think it depends a little bit on the modeling framework. For instance, Bayesian computational models are often framed very generically. And then it is a little bit easier to actually analyze them for their complexity. But I don't know if I address, if this is your concern.
Right. This was in the cases where they do have formalization, but you can't, they could be multiply realizable in terms of what kind of networks you have. So it's not clear. So one concern that I have is it's not always clear the computational complexity of a problem, because depending on the kind of architecture you may use, you could have it quadratic, you could have it order n, or you could have it log. So there are situations where the same, for instance, in cognitive science, there's a lot of representational similarity analysis, and some models that are built about those representations, some formal models, are about the relationship of similarity between those, for instance, in associative memory or in episodic memory. These kinds of models, it's not specific to what kind of realization it will have in the brain or in a neural network. And depending on the kind of realization you can have various orders of complexity of storing the same thing. Because what you need at the end is an emergent similarity structure, and that could be realized in different ways. So that's the concern that I had. In these cases, how do we sort of, is it always clear what the computational complexity of a model is?
No.
Yeah,
so it's not always clear. And because you mentioned now examples where there's models depending on what architecture you use, or maybe even what kind of encoding you assume, they may be quadratic or n or log n. Okay. And the distinction I made between polynomial and exponential time is a qualitatively different one than these. So quadratic, log n, and for the theoretical complexity theorists will say, oh, it's all polynomial. And there is, at the algorithmic level, so if you make a commitment at the algorithmic level, these distinctions become meaningful. Because you could have a particular algorithm that has this kind of running time. For instance, different sorting algorithms can have all kinds of different running times. But the kind of distinction that I refer to as the distinction between exponential polynomial, it is not sensitive, at least according to the invariance thesis, to the particular instantiation. But that only holds for this distinction. That is, on the one hand, a loss because you would say, well, but that is a very crude one, right? And we also want to make finer grained distinctions in computational complexity. And I would say, yes, that is great to do, but you can only do that at this lower level. So minimally at the algorithmic level, and maybe you even need to have particular assumptions about implementation. But this other distinction between tractable or intractable, there we do not need to make such assumptions. But indeed, that's on the one hand, it is a cruder distinction, but it requires fewer assumptions to make that distinction. So the kind of complexity, well, the kind of application of complexity theory that I discussed just now in the talk is not to use computational complexity to predict particular timing profiles of algorithms. It's more to say, qualitatively, this kind of model is utterly unrealistic. And you have to do something to make it realistic. And then once you're in the realistic bounds, you say, okay, it's minimally polynomial, or maybe it's fixed parameter tractable if you buy the parameterized complexity approach. Then within it, for particular algorithms, you may have different timing profiles. Yeah, so that distinction is, that's important.
That was great. Yeah, that was great. So I definitely wanted you to get to that, actually. So that's fantastic. And I wanted to link that. I was hoping you'd say something like this so that I can link it to the other question, which relates to some recent sort of discussions that happened on Twitter that you were there as well of, the pros and cons of Mars 3 levels, basically. And so I feel like what you just said nicely, I think can smoothly sort of transition into this. So I do wonder, so what do you think about the relationship between whether somebody maintains the 3 levels or not in terms of the distinction that you just explained?
Yeah. I want to invite also people if they have opinions on this, because I know people have very strong opinions on this. So please come talk to us about it. So I think what drives, at least from the discussion also last week, what drives some of potential disagreements is an interpretation whether or not the levels of MAR are okay. How I adopt the levels of MAR is as the kinds of questions that we can ask about a system, like the what and the how in physical realization. But you can ask these questions at different levels of organization. But I think some people interpret the 3 levels of MAR as mapping to, for instance, the computational level, say, applied to psychology is intentional level, the algorithm is the process, and the implementation is brain. And of course, I also slipped to this interpretation in my presentation because it's convenient and everybody understands it. But I also made a comment somewhere that it doesn't really matter. I could also, I could say at a neuronal level, I can ask these 3 questions, or at a group level, or even at a society level, I can ask these 3 questions. So in that sense, for me, the levels of MAR are detached from, at what level of organization. And I think different views on this leads to disagreements on the use of the levels of MAR. I don't know if there's other critiques. So what are common critiques? I can think of some, like that you can't just not specify the computational level.
So
I think Jonathan Pillow and Tony Zader. Jonathan Pillow and Tony Zader are the ones who have these kinds of. Okay, do you want to go, Jeff? Or any of you?
Just one thing, Iris, is that it's precisely to protect you from all the rabid anti-Marians that you should continue to answer the questions yourself, because I kind of agree with you. It's very hard to know what it is they're getting so upset about.
So you don't want to hear? I'm curious. Can someone channel?
If they're here, they're welcome to speak. I would say, if you read back through what Mara wrote, he oscillated a little bit between how many levels there were. Sometimes he wrote there were 4 levels, and sometimes he wrote there were 3 levels. And there's some legitimate criticism from philosophy that says, actually, you could think of there being 10 levels, and exactly where you define the boundaries in physical systems is pretty there's some flexibility there, right? Assembly code or Python or a pseudocode and the algorithm are reasonable ways of doing levels in hardware. So I think that's one legitimate criticism, but I don't think it really matters that much in the sense of what we're talking about. Okay, if there's 4 levels, fine. There's another level of explanation, and you can say that one too.
The critique that I've heard from Jonathan Pillow is against this kind of algorithmic chauvinism. So it would not like the kind of the highlighting of the importance of the algorithmic level that I think that Iris cares about. So that's the reason that I brought this up.
Sorry, can you articulate? So what is the computational chauvinism critique?
Algorithmic chauvinism. So
algorithmic chauvinism.
Yeah. So they don't like people who I don't understand them completely, to be honest, but it seems like they don't like people who focus on the algorithmic level because they think that the implementation level is the place to focus your attention.
Okay, so what I can say is that at least for the kind of analysis that I discussed, like the tractability, actually it doesn't matter how many levels are in between. Even if you say, there is no way of me knowing how to write the algorithm, this property of intractability is independent of us knowing any algorithm. It's just saying any algorithm you could possibly think of or you cannot think of, it doesn't matter. It will have this property. And I'm with Jovo in a sense that I think it does. So for me, also the question, is it really 3 levels or not, is not that important. And indeed, you can decompose functions into functions, and then you can say, okay, at what point, where is the algorithm, and where is it just zooming in on a new computational level theory? And since I adopt it as an explanatory framework, I remember that I was here before also when we talked with Martin about, is the brain a computer? And then I said, for me, it's more interesting the question to say, can we explain cognitive capacities computationally? And I see these levels as, an explanatory framework. So they're not a claim about how many levels are in the world, but different kinds of explanatory strategies.
Right, to be clear, it's not about, in my understanding of them, it's not about how many levels. It's about the fact that they don't like the focus or the stress or primacy or whatever of the algorithmic level. So it's different than arguing just how many. So there is those people who say the levels are not enough. And there is those anti-Marians who say, I don't care about the algorithmic level. And it seems like that's the type that, or we shouldn't care as much about the algorithmic level. So I think that's the kind that I find, I don't understand it quite much. But what I hear from you is that in terms of the operations that matter, if I understand correctly, you do have a distinction between algorithmic and implementations, which is, in at least in your talk, which I personally think it's valid and it's important. And I can see that even if someone didn't believe in the algorithmic level, one could either extract it or not from the implementation. So that's how I understood you, but.
Now I'm not sure what was the last point. Can you clarify the last point?
No, actually, I'm okay. There are a lot of questions, so I'm okay to go on to the next person.
Go ahead.
Yeah, can I still say something about the algorithmic chauvinism? Because this also came up in Twitter discussion about sort of what is primary. And of course, Marr really promoted this top-down approach where he said we are more likely to understand the mechanism by understanding the nature of the problem than it solves, or the algorithm than looking in the mechanism. Though he also wrote a paper in 1977 where he actually questioned whether this would be possible for all mechanisms. And I think this is lesser known, but he also himself said this may be possible for some mechanisms, but not others. And I think he calls these type 1 or type 2 mechanisms. But I personally think that we don't need to argue whether or not the one approach is better than the other. I think let us all work on all the levels. And some people like to work on the implementational level, other on algorithmic, other on computational, sometimes on the bridge. And I think such pluralism in approaches is better than fighting over which is the more important level. personally. And I have a style myself, but I don't think everybody needs to follow my style.
I personally agree with you, but I think that the challenge comes when people sort of really disagree strongly. I think John wanted to follow up on.
Okay.
Well, are you done? You are? Okay.
I could go for many more hours, I'm sure.
Sure. Jova, I don't mind asking my question after you if you want to go next.
We're all on the same team.
Okay. I wish, darling. Anyway, so Iris, so I have so many things to ask you. I was actually a tiny bit in a panic about how to do this in order because I don't want, as I said before, I don't want to hog you. First of all, I want to just, of course I agree with pluralism. Pluralism is a very deep point. It's actually a much deeper one than just being democratic. It's actually an intellectual one. But you do say in your paper that I really liked, Theory Before the Test, How to Build High Verisimilitude Explanatory Theories in Psychological Science. So you were talking about verisimilitude, right? And in there you say, I quote, generally, psychological theories of capacities, and I agree with you, should be one, mathematically specified, which you've been talking about, and two, independent of the details of implementation. Independent of the details of implementation. Okay, so it's very nice for you to be all ecumenical right now, but I actually agree with you that actually for psychological theories, and I'm going to use that term to be synonymous with cognition, and there are other people like Marcin Milkowski we've had here before, Gualtiero Piccinini, who has a new book that's about to come out, where he also makes this case that computational theories of mind, to be computational theories of mind, have to be substrate independent. Masvita, I think, talked about this too. So you do have a position that good psychological theories of capacities should be susceptible to your tractability arguments, and they should be implementation independent. You're not going back on that now, are you?
You're on to me, John. Yeah, I was reminded also, I wanted to say that, yes, I do think psychological theories, but that is a particular level of organization.
That's what we're talking about here.
Yeah, and I do think we should also be able to specify them independent of implementation, then meaning brain. And I was reminded, so last week I couldn't follow the full discussion, but I did see Masvita's presentation, and I want to say, well, I'm a functionalist. So yeah, I believe that there is a level of specification of psychological capacities that is implementation independent. And I will not go back on this. But that doesn't mean that neuroscientists who think by studying the brain they can get insights about implementational constraints. I wouldn't want to say don't do that research, because you should all do psychological research.
No, I mean they can build model airplanes as well, you know.
Yeah.
But so I have other questions for you, which is so in your book chapter, you start with the picking toppings for a pizza example, okay? And then you talk about, and I remember when I first came to the United States, it was so bizarre to me that there were 31 flavors of ice cream. You know, how am I going to choose? You know, there are menus that give you nightmares because there are so many choices. But the thing is that we don't go through all the combinations and rank them in our favorites, because as you say, it becomes intractable. So the question I have for you, and I'll follow on, is, well, what do we do when we go to a pizza place or a 31 ice cream store, and we don't spend 5 years picking our favorite flavor, right? We usually walk out in about 5 minutes, right? So what have we done? I was just wondering if you could tell me, how do we actually solve the 31 flavor ice cream problem we walk in? Because in your chapter, I don't find you actually telling me how I do it in 5 minutes. So can you tell me, how do I do it in 5 minutes?
I don't know how you do it. I actually experienced the same challenge since I'm Dutch, and I actually went for my PhD on computational complexity to Victoria, Canada. And that's where I first encountered, indeed, that you could freely pick your topics, because in the Netherlands, we don't. You just have 13 options, and you just pick from them. So that's how we do it in the Netherlands. So I don't know how we do it, but the how, well, it depends what you mean by how. Do you mean an algorithmic how?
Yeah, that's exactly, yes, I am actually asking that. I'm saying that, and it will get to my next question, because I think this is the heart of what's always bugged me in all these conversations, you know, John Langford and Ida and others, and this is why I find this so delicious, not the pizza, but the conversation. So do you think it's useful to imagine that it is an algorithm that we use when we pick a pizza flavor in 5 minutes?
I don't know. I'm going to answer a different question for now. Because, well, I picked on purpose, the classical notion from decision theory that we pick options that maximize utility. And if you have two options, usually many classical experiments are just with two options or a handful of options, then you can say, oh, okay, you can have some algorithm that just compares and it does some pairwise comparisons and you pick it. But if actually your options are indeed combinations, like you get this combinatorial explosion, then you have this intractability problem. The classical choice theory response is, we don't know what the algorithm is. It's just that people will pick whatever maximizes utility. And the point is, they cannot. If the problem is intractable, they cannot. So if indeed, well, depending, if this is our point too, it depends a little bit on your preference structures. But if your preference structure is completely unconstrained and you can have even two-way interactions, right? So maybe you love pineapple and you love olives, but you don't love them together on your pizza, right? So you have these kinds of interactions. Then already this problem becomes intractable. And I guess the upshot is, if you want to maintain this kind of model, then it basically means that we will end up with a pizza that actually doesn't maximize utility. So we end up with a pizza that is not our best choice, but we may not even know what the best choice is.
Right.
Because, well, you know, it's somewhere hidden in this complex space. And, well, yeah, we go out.
So my question then, if what you're saying is true, and I'm leading you this way, is, are we missing something about how we actually do make our choices in a 31 flavor ice cream parlor or in a pizza store, or whatever you call them? Is the sort of just good enough shortcut that we take, the heuristic, and you know, I'm doing it, right? It's me with my brain going in and picking. How should we think about that kind of decision? What are we doing? Are we? Is it some sort of heuristic? Is it some kind of abstraction, like I'm going to eat sweet or savory today, or I think I should be healthy, so one vegetable? I mean, what do you think the cognitive shortcut is that gets us out of the store in a few minutes? I mean, I know I keep asking. If you don't think there's an answer to that, you know, I think it's valuable, because an AI is going to have to one day choose a pizza.
Yeah, I think my approach is, so listening to your question, I'm reminded of how much a theoretical cognitive scientist I am. And that I am, so that this question, like, how do we do it? Maybe I go about it in a more indirect way. I'm looking at the theories we have about how we do it. And I want to know how viable these theories are. And for instance, saying, well, we do it with heuristics. This is a very common idea too. Yeah, okay, so sort of the history of behavioral economics, classical critique, right, of rational choice theory and maximizing utility. But then there's people that say, well, we do it by heuristic, and with this, this was my point of approximation. Well, Okay, so you can say we do it with heuristics, fine, there's no problem. But then there's also cognitive scientists that maintain that this level of explanation at the algorithmic level is an approximation of, of also maximizing utility. And what I'm analyzing is to what extent these different explanations are compatible. And actually, if you look at them closer, they are not compatible. They will diverge.
Right. No, I totally get it. I totally get it. I'm just wondering whether what the heuristic is a bit more meta, which is it switches it into a tractable problem. In other words, it's not, rather than some sort of, let's just satisfy and then hit a bound or switch tasks. I mean, but anyway, I don't want to go on. It just bugs me, and maybe it's just my problem. The last thing I wanted to ask you was this notion of abstraction. Ida and people working in the same domain, Ida, when they talk about sort of state and temporal abstractions, right? In other words, ways that you can sort of chunk a little bit a problem, because if you take a low-level reinforcement learning approach about actions, I mean, if I had to sort of think about going downstairs to the kitchen and worry about every ankle angle that I did and every turn that my body made to get from here down to the kitchen, it would become one of your intractable problems. So there has to be a way to sort of, for lack of a better word, Ida will attack me, chunk it into, some sort of options temporally or state abstractions. But
this pushes the problem.
Sorry?
This pushes the problem to a different problem, namely how to chunk.
Yes. So what I wanted to ask you is exactly that, which is, do you think that one of the ways that, the RL community deal with not having it be too low-level intractable by doing some kind of abstraction temporally or in state space, so you have correlated neighbors. But my concern, like in the pizza case, is the abstractions that humans use are a little bit more abstract than those abstractions, right? It's, oh, I'm just going to eat healthy today, or I'm going to only eat green pizzas. I was just wondering whether you think the kind of abstract or heuristic shortcuts that we may take in these problems are not the same as the kind of abstractions that are being devised algorithmically in the AI community.
Ida wants to say something.
So first of all, I don't want to distract too much from the main topic of your talk, as opposed to the sort of implicit sort of new discussion that opened up. But I do want to say, before responding to John, I do want to say that Melanie and a person called PO, I'm not sure who they are, they had an interesting discussion. The PO asked clarification, is interactability an epiphenomenon of P versus NP problem complexity? And this has been going on a little bit in the chat, whether it's about complexity of algorithm. Oh, you don't need to look. I'm just going to mention so that you can, I'm going to read them for you. So whether it's about complexity of a problem or algorithms. So there was a discussion about that in the chat. And Melanie's response was that I think Iris is using interactability to mean exponential time in the size of the problem. This is related to P versus not NP, but it is, but in a kind of a complicated way. Maybe she will explain. So do you have any comment that you want to make on that before we move on to the topic of reinforcement learning?
Yeah, so I can confirm that the kind of complexity I'm talking about is a property of the problem, not the algorithm. Well, of all the algorithms for that problem, not a particular one. And indeed, it expresses the complexity as a function, not of the problem, but we say the instance size or the input size. Because in complexity theory, we reserve the word problem for all the possible instances of the problem. So it expresses the complexity of solving the generic problem as a function of the size of a particular instance. Does that answer the question? Okay.
I hope so. I think this was just a clarification question that they had, and thank you for that, because there was a couple of people who were wondering whether it's complexity of algorithms versus complexity of problem. to the point you just mentioned, Melanie also said it's related to exploration and exploitation balance. We choose things that were successful in the past, but also have some probability to try something new. And I just want to say a lot of the work in episodic memory and adding episodic memory to AI models actually does this, which is that sometimes you just use whatever that worked best, or there are other kinds of things that happen, and you can capture heuristics in algorithms. So I'm a little surprised that heuristics would even be brought up as an alternative to an algorithm. Because you can have, whether you have to take the first, take the last, take the best, all of these are various kinds of heuristics that you can implement in an AI agent on the basis of
but best
using
has
command.
some meaning. But best has semantic meaning.
Yeah, but you can, anyway, yeah, you can define it. But going back to the issue of meaning, if you like, or semantics of it, you can associate an abstraction with a symbol or a sort of a word in an embedding, however you want. There are different ways to approach this. So I just want to, I don't think this relates to Iris's talk as much at this point. I'm not sure, but so I leave it to Iris. I just wanted to mention these two sort of footnotes before you respond, Iris.
Thanks. Yeah, I would like to respond, but it's a little bit tricky because I go a little bit more into intuition than in what I can formally back up. But so I think, John, that often when modelers of particular tasks make models, they perform the abstraction. They interpret the task. And they can partition what is the object in the task, or what are all the relevant features. They use their own cognition to do that, make the model, and they say, look, it's a great model, does the task. What they forget is that their own cognition was in the loop. And that ultimately, we want to explain how when we go in to get the pizza or whatever, or do
right. So they haven't
laundry,
explained anything, actually. Right.
Yeah, there is what is it, the ghost in the machine, right? So and I think some tractable results are because of this, because the modeler is still solving part of the hard part with their own cognition. And then indeed you get the heuristic. So this is related actually, because, well, I said to Jovo, I don't pick that paper, but we also had this paper where we actually analyzed. So a common critique from heuristics people is also the Gigerenzer tradition says, well, these classical theories of rationality and choice, they are intractable, but we humans, we have evolved a toolbox of fast and frugal heuristics. And using this toolbox, we can tractably make decisions. Like you say, we just go into the pizza store and we take the best, or we just take what took last time, maybe, or we took what the customer in front of me took, or whatever, some such heuristic. But the claim is also that these heuristics are good enough, right? So they're at least good enough. I don't know, that our choices, and maybe our choices are not so bad that we die instantaneously. We get around the world well enough with them. And but this assumes that somehow, well, either a learning process or evolution figured out how to configure our cognitive architecture such that in the world, when we use these heuristics, things work out well enough. Now, in that paper, we analyzed actually this claim. And so what we did is we modeled actually the evolutionary process, or the learning process. Doesn't matter because, of course, we abstracted at the computational level to analyze, okay, but how complex is it to configure a system for some environment that it will have available, this toolbox of fast and frugal heuristics, but also be able to decide well enough. And what we then could prove was that actually this configuring is the intractable part then. And I think there's a general lesson in this, that you can buy tractability somewhere by pushing it somewhere else in sort of a pre-processing step. And I think this is an important general lesson maybe to cognitive modelers, that the model you make, well, yeah, how did it get to have its nice properties?
I mean,
Well,
it did take Iris to get from a bilaterian worm to a mammalian brain 500 million years, right? So that's quite a long time.
It's nothing.
Right?
Yeah, but you shouldn't calculate
John, you're too young.
in real time. Well, that you need to calculate in generations, right? So you shouldn't calculate that in real time, like seconds.
Right. And my last question for you, just because,
okay.
you know, I did warn you that this would be too much fun. And so I just, you know, going back to the algorithmic bias that certain people are, it seems to me, reading your work and looking at the two directions that psychologists are under pressure, right? One is the implementationalist saying, you know, what they say ad nauseum is, we need to look at the constraints that the substrate imposes so that we can come up with plausible algorithmic theories in psychology. You've come from the computational side, which is to say, well, let's make sure that your function is tractable. So you're coming from the MAR level 1 side onto the algorithmic psychologists, and the implementationalists are coming from the MAR level 3 side. But would you not agree that, at least when it comes to psychological theories, we are trying to be algorithmic? We're trying to understand what the processing steps need to be on a representation to do cognition. And, you know, it's the old idea, and, you know, it came up with Masvitra as well, that cognition is some sort of algorithmic processing on a representation. So would you agree that, at least for psychological theories, we're going to be primarily algorithmic? I think I would agree with that, and that we're going to have to be as alert to the computational mathematical side that you're bringing as we are going to have to be as alert to substrate constraints from the neuroscience side. And it seems to me that if we pay attention to you, we might get there first via AI than worrying so much about the substrate level constraints.
Was that more a comment? More a comment than a question.
Yes, it's a comment, but I want to know, but you know, the pressure coming from 1 onto 2 versus 3 onto 2 in terms of Marian levels.
Yeah, I think psychological theory is massively under constraint by data. I mean, theory is just under constraint, right? And so I think we should take all the constraints we can get. So I think it's good to come from different levels and constrain our theories. I do think that the computational level, the constraint on the computational level theories is sort of underappreciated, as if anything goes on the computational level, because, you know, it's just idealization. And I think that tractability is very useful. So on the one hand, intractability is bad news. On the other hand, it's good news, because this means that we actually have a strong constraint on our computational level theories, just the principal theoretical constraint. And that reduces the space of possibilities.
With great reluctance, I'll stop there.
Thanks, John. So I'll just start by saying I have the answer to John's question, how do people choose pizzas? I have a friend who swore by the additive subset algorithm. And this was an amazing game to play, because we would be having dessert and we'd be having, like, you know, birthday cake. And I'd be like, hey, you like pickles? Put some pickles on the birthday cake. And he'd be like, this is even more delicious, because now there's more delicious things on top. And he swore by it no matter what we did. And I think it worked for him. So at least for him, it was very clear and computationally tractable problem.
Perfect.
Yeah. So I have some questions for you, Iris. You know, I was telling Ida earlier that it's very difficult for me to think of questions for you, because you're so clear and so logical that it's there's almost nothing to quip about. But I do have some kind of meta quips, I'd say. And the first comes from this perspective I have from being in statistics and then in machine learning. In statistics, we really like to talk about asymptotic analyses, right? And so basically 100 years of statistics, we're worried about when n is goes to infinity, what happens? What are the properties of our algorithms? And there was a switch in the last 30 to 40 years in machine learning where a lot of people in machine learning don't care at all about asymptotic analyses. And they say, no, we need to study algorithms with respect to sample size. And a canonical example that's come up before is something like the k-nearest neighbor algorithm, which asymptotically is perfect, and empirically for basically any sample size, it's usually a bad algorithm. And so, this goes to this whole notion of complexity theory. And reading some of the chapters of your book, the asymptotic analyses are when n is large enough, then these rules hold about the order of complexity. But I could imagine someone saying, well, n isn't that big, and what the kind of complexity theory we need to be thinking about is a finite sample complexity theory before n gets big enough to care about these asymptotic things. And that it's kind of the wrong framework to be thinking about, and we should be thinking about really finite sample n, not asymptotic n.
So thank you for this, Jovo. This question always confuses me. Yeah. So I should be better prepared since I had this comment before, but it always confuses me because I think we're talking about two different things. So in sampling, you have these asymptotic results. If your sample goes to infinity, then indeed you approximate perfectly like these kinds of results. And of course, in computational complexity, we also have asymptotes, but they're different. They're not the same thing. This is just to express. This is an analytical tool to express, time complexity. Because for finite inputs, if we take a constant size input, everything is polynomial. Everything is constant size. But this. Okay, so how can I explain that this is not the same? So maybe to ask clarification. Is your intuition that intractability only happens in the limit, and that as long as we restrict our problems to finite size inputs, intractability is not an issue because intractability is an asymptotic property? Is that the intuition?
It's not quite. My intuition is, I wonder if there's a different, it's much less well-formed than what you said. So my intuition is, I wonder if there's a different way of thinking about complexity that focuses on small n. Not asymptotic per se, but just before you get to the bigger than n naught problem. And if that's where we should focus our concerns.
Yeah. Okay, so two comments. Intractability is not an issue for very, very big n. It's already for anything that's not small n. So in the complexity, we already are concerned with intermediate size, not in the limit n. This is one comment. And the other is that so maybe it's not your intuition, but I think it's related, is that, for instance, in Bayesian cognitive science, also sampling algorithms are quite popular as algorithmic level hypotheses about processes, also how to approximate Bayesian computations. But there is also an sort of a probabilistic analog of computational complexity theory that also analyzes the computational resource demands of such probabilistic algorithms. And if you have an NP-hard problem, then everything else being equal, you also cannot approximate that algorithm with small sample sizes. You will not be able, then you actually need to have these huge sample sizes.
Yeah,
so it doesn't, so basically saying we're going to limit the sample size means, okay, then your algorithm becomes a heuristic. And with no guarantees of approximation. And okay, so then the argument about heuristics holds again. I don't know if it addresses your point.
It does, and this comes up in practice for me because I work on graph matching a lot, which is, for those of you who don't know, I have one graph here and one graph here, and I want to find the optimal alignment. And that turns out to be really hard. And, you know, we spent years and years and our code works great for like n equals 30. And then when n equals, say, 1,000, which is a totally reasonable size of a network, say, for human brains, already our algorithm, which is an approximate algorithm, is still, and we have it's an algorithm, not a heuristic, in the sense we have provable guarantees that it gets the right answer with high probability, but doesn't run when n is 1,000, because it just takes, you know, 1,000 years to complete or whatever. So I agree with you. I'm with you. I just think it's interesting that there was a shift in concern about asymptotic versus finite sample, and how that may impact thinking about cognitive theories as well. The other question I have, and this came up actually because of a paper John wrote recently, which is it's really fun to think about algorithms as kind of independent entities, and that's how I think about them. And including cognitive algorithms. But John recently pointed out that the algorithms fight for information in our brain. And I wonder what the implications of that are with regards to computational complexity, because it seems like now we want to study them collectively rather than independently. And that seems much, much harder. And already we're in trouble. So I wonder if you can tell us how to think about that.
Well, I go to my own habit. So the benefit of looking at the problem at the computational level, at least through this complexity lens, is that it doesn't matter, for instance, whether or not the computation is done by one algorithm or a collection of them in competition. What I am thinking is that implicit in this approach is that we can actually describe these algorithms. And this comes a bit back to our earlier discussion about, is the brain a computer? Implicit in these analyses is that actually we can, so what is an algorithm? Well, a step-by-step procedure, but there's a crucial assumption, namely that it has a finite description. And without that assumption, some of the results may not go through. And you may say, okay, that's a limitation, right? So, but on the other hand, this is why I think of these analyses as theoretical analyses, that we scientists can only talk about cognition or the brain through finite descriptions. So it may be that the limit on us as sort of cognitive agents studying mind or whatever the world, we are limited, that we can only explain finitely, and therefore, we have these limits on computational explanations. So one view can be, this is a limit of the computational system. On the other hand, it may just be a limit of our cognitive explanations. Anyway, this was cued by your comment that maybe the processes are so complex and messy that there is no one finite description of the process. And I'm just sort of putting on the table that I don't know if that is the case, which of these computational analyses all still go through. Just being transparent. Curious how other people think about this.
So while Jovo is inviting Melanie to ask her, as usual, top voted question. Hi, Melanie.
Hi.
There. Yeah.
Sorry, I don't mean to ask the top voted question every time. It's embarrassing.
Yes, it's a terrible, terrible weakness, Melanie, to always have great questions.
I hate it.
So embarrassing.
I wish I had some answers. Thank you, Iris, for this fantastic talk and discussion. I've been really enjoying it. So whenever people start talking about computational complexity, I start worrying about the difference between worst case, average case, kind of the most common case. I think, and I know you mentioned this on one of your slides, although you didn't go into it, but a lot of people who haven't taken like a theory of computation course don't always know that complexity, when you talk about the complexity of a problem class, it refers to the worst case instance. And an example of this is the topic of protein folding, which has been in the news recently, but it's known to be, NP hard to predict protein folding, and yet, or to do protein folding, to carry it out, and yet our bodies do it every millisecond of every minute, and they do it, and one reason is because we're not faced with the worst case amino acid. And so the complexity of a problem in practice can be very different from the complexity in theory, because you don't know what the cases are that you will encounter. And I'm wondering what your thoughts are on that with respect to the discussion, especially with regard to the cognitive problems that humans encounter.
Thank you. Very clear. And lovely that you're here. Yes. Okay. So where to start? Indeed, this notion of computational complexity that I discussed assumes worst case analysis. But worst case means, so I said before, so we define a problem as the set of all the instances. And it just means, or all the inputs, all the logically possible inputs. Worst case analysis means there is at least one, and there must be actually infinitely many inputs on which the performance has this bad characteristic of being exponential. There must be infinite, because if it's a constant, then actually the problem would be tractable, because you could just make a little lookup table for these constant number of inputs. So it must be a big set. But you're right, it's worst case. Now, you may object to say, yeah, but these worst case, they may not actually happen. They may be so they may be logically possible, but for the problems we face, they're ecologically irrelevant, say. Right? And I would say, I agree. I agree with you. And I actually think this is the solution. And for instance, parameterized complexity gives a tool to find these instances. So what are the properties of these instances that have this bad behavior? And can we assume that they don't happen? But note that if you restrict your theory to say, okay, but I'm going to assume that not all the logically possible inputs are relevant for my model, but only the ecologically relevant ones. And here I have a nice mathematical characterization of their sort of upper bounds. Then the worst case analysis for this restricted domain yields tractability. So you can still use worst case analysis is always relative to your assumed input domain. So I wouldn't say that these problems are intractable because of worst case analysis, but because of insufficient constraints on the input domain. Because if you think a particular input shouldn't be there, then well, throw it out. Then it shouldn't be in your theory. So what I should clarify is that these analyses are not about saying this is intractable in the real world, like protein folding. So I don't think memory or human common sense reasoning, well, to take that as an example, that's really intractable. It's only our theories of it are intractable. And this shows that we are currently lacking an understanding of how it's done. So the claim is not that these proofs show that common sense reasoning in the real world is intractable, just that our theories of them are.
So that's interesting. But couldn't it be that, if you look at a mechanism like you talked about Bayesian inference being intractable, okay, which means that in worst case scenarios, it's intractable. And we don't want to reject that though, because maybe we are maybe we're doing Bayesian reasoning all the time, Bayesian inference. And, there's a lot of people who think that's true. I'm not necessarily one of them, but I'll be devil's advocate here. That because in the real world, we never encounter these badly performing inputs, as you say. But you're saying the model's intractable, not the actual mechanism, but maybe that's a model that you might call intractable, but maybe it is the actual mechanism. So I'm not totally sure of the distinction here that you're making.
Yeah, I see how I cause confusion. So there may be certain cognitive capacities that are really intractable. So maybe, I don't know, the cognitive capacities for coming up with mathematical proofs, or maybe it's even uncomputable. Like we may sometimes do that accidentally, but nobody would claim that we have a tractable algorithm that given any theorem, we can tractably come up with a proof for it, because it's not possible. So implicit, and I should explicate that, I'm thinking of those capacities that people actually can do very well in the real world, very fast. And what I'm saying is that if we want to explain how that's possible, then our model of it should also be tractable. Now, it could be that the mechanism, but sort of our decision-making mechanisms, when we deal with ecologically relevant inputs, works very well. But if we put that mechanism in an experimental setting where we present it with an input outside its sort of ecologically relevant input domain, that it would indeed show this terrible behavior. And then you say, well, then the mechanism is actually an intractable mechanism. I agree with you. That's true. But my point is about how we can explain. So how can we explain that in the real world, these cognitive capacities work well and fast? And then I think, so maybe the combination is the mechanism plus the domain together, they must be tractable, because otherwise we cannot understand how those capacities can work so well and work so fast. Does that answer your question?
Yeah, I think that's right. Yeah, and I think that, that we do a lot of work on and thinking about what are the right mechanisms to explain our cognition, but we don't do as much, or maybe some people, but about the domain, thinking about what domains and how they interact with the mechanisms. Because presumably that's how the mechanisms evolved, is in response to the problems and the inputs they're seeing. And so it's a co-evolutionary process. And so these somehow have evolved so that we can do these things extremely quickly, even though in general it might be intractable, as you said. I'll stop there. Thank you.
Yeah, great. We agree.
It just sounds, Melanie, before you go, that that's just a way to rescue a particular computational formulation, but unless you have a way to break the tie, it just might be just the wrong way to think about the way we do it. Right? In other words, at least, from Iris's position, say, look, that you could, let's throw these out because they're not tractable. And you go, well, maybe you can save it, but you just have to constrain the space of inputs. Well, how are you going to break the tie? How do you do it?
Are you asking Melanie or me?
Either of you. How do you do it?
Who's you?
I didn't understand. Tie between what and what?
Between it just being the wrong computational model versus being rescuable, but having to come up with some other constraint.
Well, you can't know.
Right.
You can't know. But this was my point about that ultimately theory is underdetermined. So it's not that this approach sort of gives you a procedure to figure out the true theory. But it puts some constraints on what can count as good explanations or not. I don't know if it addresses that. I also didn't understand John very well, Melody. But I don't know.
That was the question. That was the question: is how does one have a scientific algorithm to use constraints from the various directions to march towards some insight into how it's happening? So I was asking that question, which is, how does one take these insights and march towards what's actually done algorithmically?
Okay, so you say, so now you have these insights. Now, what is the procedure to use these insights to now make the theories that actually satisfy these constraints. That's what you're
Yes.
asking me. Okay, I'll
Yes.
tell you, there can be no such algorithm. Because what you are asking is if we can algorithmize science. And I think
Yes,
that's
that is exactly what
indeed. And this is other work. It's in the new year, I'll have it out. So actually you can use computational complexity theory also to apply to science and how we reason scientifically from data to explanations. And I think it's impossible what you ask.
So
Sorry.
just
good. I wanted to. That's what I was trying to. I was exactly asking that question based on Melanie's question, which was hiding underneath. Would there be a way to algorithmize the very scientific process of marching towards the right theory? And you've answered to me, actually, no, which is fascinating.
Sorry, I'm just going to say, so to Melanie's point, and I'm a little confused now about John's question and the fact that Iris understood it. I'm not sure if I did. I'm confused by the fact that you understood it as much as by the question. So if you say, hey, here's the theory and here are the constraints, and then you say, hey, theory A, B, C seem to work with these constraints, all of them, right? And so that could be a challenge. So one thing to do is, all right, we're going to generate new, I'm talking from the perspective of philosophy of science, I guess. Then now I'm going to generate new challenges and see which of the theories can still survive under it as opposed to the other. And so this process goes on until one of them fails or two of them fails. And often in my experience, the one experiment can make two of them fail easily. But then somebody else might say, but that was because of this constraint, but maybe in this other condition. So this process goes on until some theories fall out. Do we ever land on a true theory? I guess a lot of people in philosophy of science will say no. And the best that we can do is to just, figure out what we have. Popperians would be in the falsification category. And then Lakatos people would be like, forget about it. So I think there are different approaches in the philosophy of science to this. But I am still with Melanie that, and I think it's a very key point that Melanie brought up. And sometimes problem seems NP hard without the constraint. Let me put it this way. Sometimes an algorithm seems intractable in the absence of constraint, but not with the constraints, right? But then if you want to break tie between different algorithms that with those constraints are working, then you have other things to do. But to falsify something, you would need to, show a situation where it fails. So it's not that it's impossible to falsify an algorithm. So that's the thing that I want to push back on.
Yeah, can I clarify? So, because at first I also didn't understand John. And I still agree with Melanie. And I don't think what John says is an argument against what Melanie said. I don't. But I think, John, correct me if I'm wrong, that John misunderstood what we said, or that we suggested that there was a procedure, that if you have these insights that, okay, in order to get a theory tractable, you need to figure out what is its domain, that there then would be a procedure to do that. And I'm just saying, no, there is none. But I don't think Melanie was arguing there is one. Does that clarify? The other thing about falsification. Sorry.
I wasn't saying she was arguing it. I was just wondering, to your point, that yes, one can come up with alternative explanations of the intractable to tractable transition. But when we're trying to come up with models of cognition, I was just wondering if there was potentially a way to at least pseudo-proceduralize the process that we would be more likely to converge on the correct model of cognition. That's all I was asking.
Okay. But there I think there is no better procedure than what Ida describes, and that is to hypothesize a domain, where I would say not just hypothesize a domain, but actually to formalize that hypothesis and prove that it indeed buys you tractability, because I think currently too often people hypothesize the domain, hypothesize it solves tractability, and then go to testing. So I think that step shouldn't be skipped. Then indeed you can start and test whether or not these constraints hold, or whether under these constraints the behavior is as predicted. there I do think it's still tricky for these high-level theories, like for instance in Bayesian theories that postulate such a network, right? They postulate that we already carve up the world in a certain way, such I could say this is a node or this is a belief. And of course, we don't have access to these mental states. Like the theories are often about unobservable mental states. So I still think there's often lots of extra bridging hypotheses needed between these theoretical constructs and whatever experimental apparatus that we use, that even just straightforward falsification may be difficult. But I don't think we have. I don't think we have a better way. Yeah, sorry. Please, Ida.
I'll just follow up to what you were saying, just that for philosophy of science aficionados, there's the famous sort of series of papers, Why I Am Not a Bayesian, and all of those for the same reasons that Iris was mentioning. And also I just want to say another thing is in reinforcement learning, there is also provable guarantees for the convergence of a particular algorithm to solve a particular problem. And so a lot of the math goes into having provable guarantees. It's not constrained by neuroscience per se, it's just the fact that there is a solution, so to speak. And I think that those are also interesting. And in the lemmas and in the proofs, sometimes you do have some constraints or so I just wanted to mention that is another formal theoretical approach to provable guarantees. Hello, Brad.
Oh, can I just say one more thing? So one thing that has come about in computer science is that if you can add randomness to your algorithm, you can change the complexity class. That some random methods can do better than deterministic methods on some of these complexity classes. And I'm wondering, randomness is obviously a super important thing in the brain, as far as I can understand. And I'm wondering if that's something that comes up in your research.
Yes, it does. And like the P is not equal to NP conjecture that you are familiar with, Melanie, there's also conjectures that probabilistic polynomial time classes like PPP or RP are actually equal to P. And if that is the case, which is widely conjectured, that actually randomness cannot buy tractability. So that doesn't mean that randomness cannot make certain computations more efficient, but that's within the polynomial realm, but not to bring you from the non-polynomial to the polynomial realm. Does that answer the question? A bit of bad news, but sorry? You're muted.
Internet connection is stable.
Sorry, I was having trouble unmuting. Yeah, I mean, there's a lot more to say there, but let's go on to Brad for now. But thank you.
We don't mind hearing more from you. We don't mind hearing more from you.
Yeah.
Well, there's, I don't know, non-polynomial NP and P. I mean, P is part of NP, right? And it's not clear that NP and P are actually different classes. That's still an unsolved problem. But in fact, randomness is what gets from NP, is what solves NP problems in polynomial time, because you're able to randomly guess solutions. That's what NP means. Go ahead.
You can accidentally guess the solution, and then in polynomial time, you can recognize it. So NP means that if you guess correctly, you can know that you guessed correctly. But that is not the same as in polynomial time, making sure that your guess is correct. And so it's true that NP stands for non-deterministic polynomial time, but non-deterministic algorithms are not the same as probabilistic ones. In theoretical computer science, the non-deterministic actually makes all possible guesses in parallel, or magically makes the right guess. But I don't think that matches what we intuitively mean by randomness, and it's not what sampling algorithms do. So actually in theoretical computer science, we would say that non-deterministic computation is not a real model of computation. It's just some sort of, what is it, a theoretical idea to define the class NP.
Okay, thank you.
Maybe we need to discuss, okay, well, maybe we discuss more later. Okay.
Ida, did you want to read John Langford's question?
Sure. Let me just quickly do that before hearing from Brad. So John Langford says, it seems there are two levels of computational hypothesis. One is that computations should not be from an interactable class when scaling is important. The stronger hypothesis is that the computation should not be much worse than the best possible computation. I'm just asking it now because it's related, I think, to Melanie's point.
Is this a question for me?
Right. So I guess.
Can I comment?
Yeah, of course, exactly.
So whose question was it, John?
This is John Langford.
Yeah. Okay, thank you, John. Could it be that this distinction, so the best, so I think I understand the distinction. So you say, well, okay, if the problem is hard, yeah, I just cannot do better than what I'm doing, or I cannot solve intractable problem tractably, but I can do as best as I can. And if I'm doing the best possible, then that's good. And I think this makes sense from an engineering or problem solving perspective. So maybe from an AI perspective, that makes sense. But my interest as cognitive psychologist is not to solve a given hard problem. I want to, as one may call a reverse engineer, and say, I have here a system that is presumably solving problems, and I don't know exactly how to characterize the problems, which actually characterize its capacities, what they are. But given that the system is doing it well and fast, I'm assuming these problems must be tractable ones, and I'm figuring out the problems. So contrary to, for instance, in computer science or maybe AI, I don't know, where you're given the problem, you say, this is the problem, solve it as best you can. And if you're given an intractable problem, well, that's your reality. But that's not the modeling reality that I see. Where we say, well, we have a real world system that is solving problems, and we want to figure out how can we characterize the nature of the problems that it's solving, which are the computational level theories.
So John is not here. He had to go take care of his kids. But given I know how he thinks, and again the question that he says, I'm not sure if I saw the complete correspondence. I think his point was that it's one thing to say don't take solutions from an interactable class. A stronger hypothesis that the computation shouldn't be much worse than the best possible computation. I think it's a normative assumption about biological computation in this case. For instance, a model of memory shouldn't be worse than log n in complexity. So that's that kind of an assumption that we should have, like, if there is a problem of how to store n number of experiences in a way that's retrievable within a finite number of time, within this kind of constraints, then potentially, I think maybe what he's saying is like normative models, which is that then, go ahead.
It's interesting. I understood it differently just now. So this is interesting. But is John then arguing that the algorithms that we use are the best possible? Because if that's the case, then evolution or God or whatever you believe figured out how to give us the best possible ones. And I think that is an intractable problem for sure. So right. Yeah, it's a very strong assumption that we would have the best algorithms.
It says shouldn't be much worse than the best possible, not that it is the best. So okay. Slightly different.
But I am pretty confident, according to some definition of not much worse, that one could argue still figuring out what those algorithms are is hard.
And Iris is what is interesting, right? And what has gotten some trouble in this field is in certain sensory motor situations, it's amazing how near optimal we are, right? We are basically for Q integration Bayes optimal. And, you know, if you look at something like the electron transport chain in a cell, it's remarkable how close to absolute optimal it is when physicists have looked at it. So in other words, I think one of the interesting things has been when it comes to modeling cognition, and I disagree with it actually, that there's a belief, well, we've had so many hits with evolutionary optimization and through the sensory motor system, but then you get the whole Kahneman world and that we just don't do things optimally and we make all sorts of cognitive biases. And then the question is, can we reframe them so they're another kind of optimization? So it's half true, but in other areas of evolutionary biology, it's remarkable how optimal the systems are, right? And so the transition is a puzzling one.
I just want to add one little thing to what John said. So the whole area of bounded rationality, when we are using normative computational models, would actually be very much on your side, saying that some of those things that some people might see as suboptimal are actually boundedly rational or optimal under certain under certain constraints. So I think it comes back to the issue of constraint that Melanie brought up earlier, that I think is the assumption of normative computational models also in psychology. That in fact, some forms of mental illness, some forms of bad working memory performance is actually rational performance or optimal performance given the constraints, let's say noise in the PFC or whatever, however you want to model sort of your constraints, for instance. So I think that just wanted to make a small comment.
Do I still respond to it, or do we give the word to Brad?
Your choice, your call.
Okay, I'm curious what Brad has to say.
So it's wonderful to speak with you, Iris. I like that you ended your talk with a positive note about ways out of the intractability vortex. So I work to some degree on the sensory side. And one of the things that I've been spending a lot of time thinking about is ways that the sensory system helps to chip away at the intractability problem by reducing information, basically trying to deliver to whatever algorithms are being used, at higher levels, a set of representations that are easier to work with, right? And so, with the assumption, for example, that discrete state representations are a lot easier to work with than continuous ones, that, there's a good argument there that, our sensory systems are working to construct a discrete version of reality to some approximation. It's not obviously completely discrete, but that, that dealing with intractability could be a really good argument for why some cognitive operations, at least, maybe even a lot of cognitive operations function in a more or less discrete space. Does that seem reasonable to you? Or also?
Yes. So I have questions. So intuitively, yes, but I also see problems as usual, because. Yeah, so very abstract. So if a problem is intractable, and this has also been a response from Gigerenzer, right? What is it? Less is more, or frugality, like throwing away information may make things more tractable. But the thing is that if you have intractability at the computational level, that can't be the solution, because if it were the solution, then there would exist an algorithm that could do it tractably, namely the one that just ignores the relevant information. But if we have intractability at the computational level, that algorithm just doesn't exist. So to me, this seems like a proposed solution where you say, oh, but if I just come up with the clever one that chunks the information in the right... Yeah, but the proof is there is none. It can't exist. That doesn't mean that our vision doesn't chunk or doesn't filter. It does. Probably it's also part of the explanation, but it can't be the explanation. It cannot be the trick. Yeah, I don't know if maybe I'll come back to also John's point, and then maybe a question to you. Is that because I said before, well, that would be very big claim that that we have these very good algorithms, or even the almost best, or close to best. And then John says, yeah, but we do. And this is also the point of, well, but we do have these remarkable abilities. And maybe even motor control, optimal motor control models, they do very, very well in describing. And then I think, okay, how is this possible from my perspective? Well, the only way that's possible, as I see it, is that somehow our world is damn friendly to us. This is the only, so somehow it must be that, maybe linking to embodied embedded cognition, that there's something maybe in the relationship between our bodies and the world that make figuring out those optimal control problems actually a piece of cake.
That's almost mystical, though, Iris.
Yeah, well, well, I don't know. I mean, there's structure in the world. We had this discussion before. I would say it shouldn't stop here, right? We should then figure out what this structure is. So I wouldn't stop there. But anyway, so going back to Brad, if such an idea saying that it's not just something that vision does or attention does, but something in the fit between what vision and attention does and the world, like could something like that work from your research area?
Right. Yeah. So I guess one of the things that occurs to me is whether or not we're talking about necessarily something that's optimal or close to it, versus on the other end of the spectrum, you can just have better than nothing, right? So you can just push your algorithm away from. You may not even be worried about whether you're approaching optimal or whether you're close to it, but just you've made an improvement relative to, the N-1 version of your generation, right? And the other side of this is whether or not you are optimizing for, maybe I shouldn't use the word optimizing because that automatically puts you on that end, right? But whether you're improving with respect to learning versus making decisions, right? And so with learning, I think of your perhaps throwing away information to build better representations that make it easier to create structures that make decisions easier. So like solve the intractability problem for, approximate some kind of, and there's that word, approximate some solution to intractability for future decisions that you will make by making cuts to information during the learning process for all of the things that are leading up to it. And so, but I take your point that we're not talking about here finding the correct algorithm for all possible worlds that you might inhabit, right? That we're talking about a system that is geared towards specific kinds of information that are more behavioral or let's say ecologically relevant to you. Like, for example, we're very tuned to certain velocities of motion, right? Like we can't detect a blade of grass growing. We also can't detect a bullet speeding by, because these are not typically things that have been useful to us. So we develop we develop receptors that are sort of tuned into certain ecologically relevant capacities. And so that's just one more of these ways, I guess, in which, the system over time is kind of chipping away at the sort of pedestal of intractable cognition by just with a sort of million little cuts, making the representations that we build easier to deal with. But I don't know if I'm just sort of iterating, the heuristic fallacy thing that you were talking about before. That's what I don't quite know.
Well, I think there's two ways of saying what you say, and I think, and maybe the one is the one you mean, and the other is the one I mean. So the one is, so we chip away, or we figure out how to sort of carve up the world in a way to make the subsequent processing easier and better. And this is what I think doesn't solve the intractability problem at the computational level, because it isn't it's just a different kind of algorithm. But if you say, no, this computational level, we are solving it in our world. So we will be dealing with certain relevant inputs, and the carving up is optimized for the kinds of inputs that matter for us. that I think can solve the problem. But these are not the same. I don't know, it's subtle, but these are not the same thing. I don't know if that's clear. Maybe
Yeah.
I saw Melody nodding.
So I guess so. Go ahead, Melanie.
No, I was going to, yeah, I think you're right. We carve up the world in a way that has been useful for us. And I think the world also presents us with a friendly way to carve it up. But I really liked Brad's point about how the decisions that we make are not necessarily optimal for like us immediately, but we're also optimizing for our future self. That we're doing something that will help us, say, by learning, that may not be completely optimal for doing something right now, but maybe helpful to us later because we've learned something. So this is sort of, there's more on this exploitation versus exploration idea that also comes up in AI very centrally. It's like, how much resource do you spend learning about something as opposed to doing the thing that's going to get you the biggest payoff right now?
And so, do I still comment? Yeah.
It's your show, Iris.
Oh,
you answer
such
everything.
pressure. Yeah, so why I didn't comment on the optimization was I forgot to comment on it because I'm not sure if the assumption is that optimality causes intractability, and then I want to clarify that it doesn't. But maybe that is not the assumption. But maybe still good to clarify also for other people listening. They may think, oh, intractability is because of optimizing something, and it's not the case. Actually, classical NP-hard problems are not optimization problems at all. They're just decision problems. They ask yes or no questions. Can I do this better than that? That can be intractable. Okay, so that's about optimization. But your point seems to be about two different classes of problems. Like, do I want to do something great now or good enough now, or do I want to have something good enough in the future? And maybe the question back is that I don't. So I think, yes, I see that these are different problems, but I don't know how they are relevant for the point. Because I would think, yeah, we also have vision and we have memory and we have reasoning and we have all kinds of different capacities. So I'm not sure.
I think maybe, I don't know if this is what Melanie was referring to, but it's related to something that Brad had asked as a separate question, which is we have lots of constraints about time constraints of how to proceed now. But the question about how to proceed later, I think, is biologically maybe have more to do with space constraints, in that how to decide what to do later. Ideally, I would have stored everything I've ever seen, all of my past experiences, and then I would use that to make a decision about how to decide later, about how to act later. And we can't do that. And so those space constraints are really serious for updating our decision rules, basically. And the time constraints are really serious for acting and like implementing the decision rules. So it's this difference between kind of learning and inference. And they're both algorithms, but they seem to have very different kinds of constraints appropriate for biology.
Okay, I understand now. Thanks for clarifying. I'm also curious if we covered the main questions also from the audience.
I think we got a lot of them. Does anybody in the audience have any further questions that are urgent? So I know it's pretty late for Iris.
Oh, indeed. It's good that I had some coffee still.
Yeah.
So some folks just mentioned under their question that the answers have been hashed out. So there were some questions that I think that they were answered. One thing that Alex G asks is, can you give examples of successful parameterization?
An example of successful parameterization. a very simple, you mean in a cognitive theory? No. But I can do it for a simple computational problem. Is that okay? Is it, Alex?
That's great.
So, for instance, if you take the traveling salesman problem, known to many people, but if not, given, let's do the Euclidean one. Given a set of points in the plane, say on paper, a piece of paper and points on it, and now draw a tour through all the points, starting and ending in the same point, a closed tour, that minimizes the overall length traveled. Yeah, so it's a Euclidean traveling salesman problem. That's intractable. So the computational resources required grows non-polynomial with the size of the number of points. However, if, and this is easy to show, that actually for the parameter, if you take the point set and you look at the outer boundaries, also called the convex hull, so as if you would put like an elastic around the boundary, and say all the points that touch that boundary, you call them the convex hull, and the other points are the inner points. Now, if you take the number of inner points as the parameter, then actually solving the TSP is fixed parameter tractable for this parameter. So having few inner points, the fewer inner points, the easier it becomes to solve. Very intuitively, if you have 0 inner points, you just follow the outer rim. If you have 1, you just have to travel once to the middle, and for the rest you can follow the outer rim. That always gives you the shortest true. And if you have 2, then you just need to figure out how to insert these 2, and for the rest you can always follow the outer rim. So it's just an example of a simple intractable problem and a parameter. Does that answer Alex's question?
I don't know if they're here.
Okay.
They haven't responded. I think it's 11 past 6 p.m. in the East Coast, and I'm guessing it's very late for you. Past midnight?
Past midnight here.
Okay.
So let's wrap up.
Yeah, before we all turn into pumpkins. No, well, not us yet. So thank you so much. Does anybody want to say some final words or such?
I had a last question for Iris.
Please go ahead.
So I'm just trying to, in the field of motor control and motor learning, there's always been this tension between people who want to be more normative. In other words, they want to sort of theoretically guess at the function and the computation, and others who try and more experimentally, I think this is something that Ida was getting at, experimentally discern the algorithm. In other words, do it through experiment. Now, how is this ant finding its way home, right? Or, so when you got asked that question just now, could you come up with an example for cognition? And you said no. Would you put yourself out on a limb and guess whether, when it comes to the modularity of cognition, and I just saw somebody put a Galastel quote in the chat, that we would be better maybe just empirically trying to find out what the just good enough algorithm is that people are using, rather than trying to go through a series of potential computations normatively and then making sure that they're tractable, etc. Do you think as it gets to be a more difficult problem that algorithmic search through experiment is going to be better, the same as a more normative approach? What would you, as a psychologist, see the difference between a sort of more experimental Marian 2 versus let's be normative and try and work it out?
Yeah, I don't see them as in competition. So I think experimentally you may come up with conjectures. Like you could say, hey, I'm looking at this, so maybe you have an experimental task and you see different conditions, that in these conditions performance is way better than in the other it crashes, like either people take long or performance is horrible. And you say, what's different? Oh, this thing is different. That may give you a hypothesis about which parameter may be relevant. But of course, then to show that for your model, but of course you can only do this if you have a model, whether or not it does, then you still need to derive. So it's not that the experimental observation shows you that this parameter, for instance, is relevant for fixed parameter tractability, but it can give you conjectures about which parameters may be useful to
But
look
experiments can give you that, right? I mean, experiments can give you an idea of what error matters, you know, what particular variable matters. In other words, you can take a guess at the variables that matter and even fit to those data. I'm just wondering.
But these
You know,
are
obviously-
observations. They're not explanations of a capacity. So we're back. This is the theory before the test paper. So you say, well, I can see that this map, yeah, you can see that if you manipulate this, it has that effect. But that doesn't show what decision making is or what motor control is. And to explain these capacities, we need to have models of the capacities. And these observations can give you hypotheses about which parameters in your models are relevant, but they don't, the observations in themselves aren't explanations.
Well, I mean, that's a longer conversation about
and
whether,
it's after 12 here.
Yeah, about whether, you know, the difference between an explanation, a model, a theory, and a hypothesis, right? In other words, yes. I mean, I thought you were asking for more. I thought you were, the kind of model that you're talking about are more elaborate than the sort of lower level explanations that people might derive from experiment.
Yes, maybe I can clarify this, and this is maybe still a bit my AI upbringing. So for explanations, for me, they need to be in principle show how the capacity could be computationally realized. And this is quite a high demand for an explanation among psychologists. But indeed, that's what I would require. So this is why such observations, for me, they are merely also constraints on this explanation, but they are not themselves explanations.
So until the Darwin's Origin of Species was turned into a computational version, there was no explanation in Darwin's Origin of Species.
Listen to Leslie Valiant, and he would say, yes, indeed. We don't have a good explanation of evolution if we cannot computationally simulate and check that our explanations indeed make sense.
That's what I wanted you to say. I think that's quite a high bar, to be honest.
It's true. Yeah. I also, if I can still say something, it was lovely being here. And it was very nice to finally be on the Salon and to have this conversation with all of you. I also look forward to still seeing what's in the chat. And yeah, and if people, I also want to say, if people still have questions for me that I didn't get to answer, feel free to poke me on Twitter.
Thank you so much.
Thank you all.
Clapping.
Thank you, Iris. That was awesome. Thank you very much.
It was a dream come true for us to have you here. So we are very excited. I was a little off today, but I feel very fortunate that this is how I'm ending this week. This is a fantastic, it was a fantastic discussion. I love the references that came out. I really appreciate, especially Melanie's contribution, both in the chat and your wonderful questions. Thank you to Kanaka and Brad and Eva and Claire. For various behind the scenes activities and clarification and questions. And thanks to Worldwide Neuro for having hosted all of our sessions. We're thinking that this would be the last, you will be, Iris, our last guest of 2020. And next week, we're probably gonna do a wrap-up session just to like take a look back at the year and take a look back at the wonderful 14 sessions that we had and sort of close the year with a discussion, like the wrap-up discussion that we had a couple of months ago. Yeah, it's been such a privilege to have you here and such a fantastic discussion. Thank you so much.
Thanks, everybody. Have a great week.
Thank you.
Good night.
Take care. Thanks, everyone. Bye.
Bye.